Hello everybody and welcome back to the channel. Today we're going to look at the fundamentals of exercise testing, and I'm going to introduce you to Wasserman's gears and the way in which we do exercise testing to analyze and understand human performance. Now, Wasserman's gears is this diagram, and it was developed by the late great Carmen Wasserman, who sadly passed away last year, but he's had a towering influence over our understanding of exercise physiology. He is, of course, the scientist that coined the term anaerobic threshold, and for my money, this diagram, developed in 1967, is the best diagram of how exercise actually works, or at least how aerobic exercise actually works. The body is depicted as a series of gears or cogs. So we have the muscle, the cardiovascular system, and the respiratory system, or the lungs. And you can see O2 flowing through the lungs, through the cardiovascular system, to the muscle for consumption in the mitochondria. CO2 gets produced and subsequently expired. And the great thing about this diagram is the more you look at it, the more details get revealed. So you've got the peripheral circulation, pulmonary circulation, you've got things like pyruvate being broken down to lactate, you've got phosphocreatine being broken down as well. And then you've got things like how ventilation is calculated. You've got alveolar ventilation plus dead space is equal to the expired ventilation that you actually measure. And these things keep revealing themselves the more you look at it. There is some criticism of this diagram, though, in that it doesn't include the brain. But I would argue that it really is there, and I think Carmen Wasserman definitely knew it was there because he's done an awful lot of work on respiratory control, which of course requires you to understand the brain's role within it. So muscle activity, the only way you get muscle activity is by activating the motor cortex, or if you're doing it externally, by stimulating the nerve or the muscle. So you have to activate it somehow, and in the normal case of affairs, that's with the brain. Cardiovascular control occurs in the brain. And of course, respiratory control also occurs within the brain, and you can hear that happening right now. What I'm doing is voluntarily extending my expiratory phase, and therefore I'm able to talk to you. What I'm going to do in this particular tutorial is talk about the muscle gear, because I'm going to argue that all exercise testing ultimately involves spinning this gear in a way you want it to be spun in order to understand human performance. So what do I mean by that? Well, there are various types of exercise tests that we can do, and in the gears model we can understand them in this way. So first of all, you can spin that muscle gear as fast as you possibly can. And when you do that, you're doing all-out exercise, so things like the Wingate test, maximal voluntary contractions if you're using isometric exercise, and of course the 3-minute all-out test, which I introduced you to a few weeks ago. That's spinning the gear as fast as possible, really useful for establishing what we might call anaerobic parameters, fatigue mechanisms, and, as we subsequently discovered, aerobic parameters too. Then there's spin the gear at a fixed rate, and to do that you'd be doing constant load exercise testing, and the series on VO2 kinetics I've recently produced takes that on and describes that in detail. Constant load exercise testing, really good for studying the general physiological response. Then you can do exercise tests which spin the gear up gradually faster and faster, and that's ramp and incremental testing and all of the variations thereon. So an awful lot of tests are based on this progressive increase in exercise intensity, and there we have a plot of a classical ramp test protocol. Then there's getting tests to spin the gear repeatedly with periods of recovery, and that's where we introduce intermittent exercise testing, and this can be designed around whatever it is you might like. So it might be interval training that you're trying to study, or it might be the work rest patterns in a particular sport activity that you can simulate in the laboratory or possibly in the field as well. So there's intermittent exercise tests. Then there's let the participants spin the gear themselves to achieve a particular goal. In other words, do a time trial. And here we see Dr. Michael Hutchinson on a Brompton time trialing, and you can see that he's in an aero position, and that's almost certainly saving him at least 7 to 10 watts. Quite why he's dressed like Angus Young from AC/DC is beyond me, but nevertheless you can do a time trial on pretty much anything, it seems. And then there's the RPE clamp approach. So what you do is you set a particular level of effort perception on some kind of scale, and then you measure how fast the participant is spinning the gear to achieve that level of effort perception. And that's the basis of self-paced exercise tests, which became quite common about a decade or so ago. What I'd like to do is go through some of these tests in a little bit more detail. And we're going to start with ramp tests. Now, a ramp test, as the name implies, simply starts off with 0-watt pedaling, so no resistance on the ergometer. In this case, we're on a cycle ergometer. And then we gradually increase the power output, and we keep increasing it until the participant reaches task failure. At that point, we can measure things like VO2 max. Prior to that, we can measure threshold, so we can measure the gas exchange threshold, the respiratory compensation point, by looking at the relationship between VO2 and VCO2 and its ventilatory equivalence. And ramp testing is really useful, and incremental testing as well, if you want to look at blood lactate response, is really useful for establishing the broad parameters of the aerobic system. And that's obviously been taken to its ultimate conclusion with Wasserman's 9-panel plot, because what we have here are a bunch of plots that can be used to diagnose and understand exercise limiting conditions. And there's a whole series of flowcharts by which you would establish and understand what the underlying pathology of exercise limitation is. So we have the VO2 VCO2 panel here. We have a cardiovascular panel with heart rate and O2 pulse on it. The V-slope panel, the ventilatory equivalence panel, a ventilation panel, the respiratory compensation point panel, if you want to call it that, the end-tidal gases panel, which would also have arterial blood gases on it if you were to measure those as well, a respiratory exchange ratio panel, so looking at the metabolic response, and then the tidal volume VE relationship, looking at if there's any respiratory limitations or ventilatory limitations to exercise. And you can compare all of these plots to what the normal or average response in an individual is, and then look for limitations. These plots have been criticized a little because they tend to be heavily biased towards minute ventilation and ventilatory responses, but you can swap those panels out for other things if you want to look more at the cardiovascular system, for example. So there's nothing stopping you doing that. Wasserman's 9-panel plot was built this way because it was, and still is, a pulmonary rehabilitation facility that was running those tests. But then we move on to constant load tests. And the thing about constant load tests and their relationship to ramp tests is what a ramp test is essentially an infinite number of constant load tests bolted together. And you end up with a smooth increase in exercise intensity. A constant load test, of course, is one step increase which is then maintained. And it's the best way of actually measuring the physiological response to any particular challenge. And we talked about that in detail when we talked about the VO2 connectors, because you could use any variable you wanted using a constant load test to understand the physiological response to any exercise challenge of any duration you wish. Of course, constant load tests can also reveal differences between exercise intensities, and you can measure those and see those things play out. So moderate exercise below the lactate threshold, we see steady state responses. Exercise between the lactate threshold and critical power, heavy exercise, you can see the slow component we talked about a few weeks ago emerge. And then severe intensity exercise, you see a large slow component and the participant reaching VO2 max and task failure. And you reach task failure faster if you exercise at a higher exercise work rate. And that's the basis of the power duration relationship. But you can see here, of course, constant load tests can also be used to establish a marker of performance, time to task failure. And that can give us a lot of information and about interventions, particularly in the severe domain, because you can pretty much guarantee you're going to reach task failure somewhere between 2 and 20 minutes into the exercise challenge. So it's a workable exercise test to look at endurance performance. And that's been very, very heavily used in the literature. But there's a bit of an issue, and there's been a debate in the literature about whether time to exhaustion trials are really any good and whether time trials are a better measure of performance. Now, I'm not going to draw any conclusions about this as such. You can think that one through for yourselves. But one thing I would say is that time to task failure trials are not time to exhaustion tests, and they're certainly not time to fatigue tests. Now, I'm every bit as guilty of using these weaker terms as anybody else, but we can't really call it time to exhaustion unless we actually demonstrate that something has definitely been exhausted, and we don't normally do that. And we certainly can't call it time to fatigue, because fatigue is a process that can lead to failure. It is not an event in itself. So the correct terminology should be time to task failure. Constant load tests don't require any pacing, but they do have a coefficient of variation for time to task failure of perhaps plus or minus 10%. And given that in the sporting world gold medals are determined by differences of performance of less than 1%, that sounds pretty weak. But out of context, that's not necessarily the case. Time trials do require careful familiarization, so you have to get your participants in to practice them several times before you actually perform them experimentally, but they have a coefficient of variation that's much smaller, between 1 and 2% typically. But if you look at the effect of an intervention with a time to task failure trial versus a time trial, the two tests will essentially reveal the same information but with different numbers. So either type of test can be used experimentally to reveal the effects of an intervention. So for example, here's a panel I showed you last week looking at the effect of priming exercise. So this is the control condition with no priming exercise. This is after a bout of prior heavy exercise, and you can see that time to task failure, we've stupidly called it time to exhaustion there, has been extended by 60% here and about 30% in the other two conditions. So a very substantial improvement in time to task failure. When we did exactly the same intervention, but this time used a 5-minute time trial, here we see the change in mean power output. So it goes from approximately 330 watts up to almost 340 watts. So that's a change of about 3%. So we've got 30% here and 3% here. But because of the difference in coefficient of variation between the two tests, the coefficient of variation for time trials is almost 10 times less than time to task failure trials, the information both of these things give you is the same. In other words, the tests have the same degree of sensitivity. And that was shown by Aman and colleagues in 2008, and I'll put a link to that paper in the description. Another criticism of the laboratory tests that we do is that these aren't how tests are, or these aren't how things work in the real world. So do they mean anything? And the obvious one is that constant load exercise and time to task failure trials don't occur in real life. That's not how sports performance works. I would argue that that's not true necessarily, because if you think about the mountain stages of a Tour de France, if you're shelled out the back of the peloton, I would argue that you failed the task being stay in the peloton. So you can measure the time that took you, and therefore that's a time to task failure trial. But also, of course, we have the wave-light system in athletics now, which is causing all sorts of controversy, but that allows you effectively to perform constant load exercise during actual performance. So the other thing to point out, of course, is that actually simulating performance is not necessarily the purpose of these laboratory tests of human performance. They are trying to work out how big a change in performance might have occurred with an intervention. So here's a question that I'm going to pose myself and answer, so don't worry, this is not a test. What's the most realistic performance test that's ever been done? And you could have a debate about that, but I would say that Huberger and et al. In 2017 was probably the most realistic I've seen, because what they did was they looked at the effect of EPO administration on cycling performance. So they had a randomized double-blind placebo-controlled trial with half of their participants on EPO, the other half on placebo, and they kept taking that for 3 months, and at the end of the 3 months they did a race up Mont Ventoux. They had 110 kilometers of cycling in the valleys to simulate the first half of that stage, or what would be the stage in the Tour de France, and then they got the participants to collectively race up Mont Ventoux. And really interestingly, they found no difference in performance between EPO and the placebo condition. So both achieved the race time of about an hour and 40 minutes on average, and there was no statistically significant difference between them. So the conclusion there is EPO does not affect cycling performance. Not so fast, I would say, on that one. First of all, there's two reasons to doubt the veracity of that finding, and I don't really want to dunk on Huberger. I've written about this before. I'll link to the blog that I wrote. But the first thing is, look at the time. It took them an hour and 40 minutes to climb this mountain after having pedaled for 110 kilometers. So that intensity of exercise is probably, if not in the moderate intensity domain, probably in the lower regions of the heavy intensity domain. In other words, the cardiovascular and muscular systems are not being stressed maximally by this exercise task. And as a result, it's unlikely that you'd see EPO demonstrate its effects because you're not pushing VO2 max. The other thing is a research design thing. They got all of their participants to race each other up the mountain. That means that the EPO group and the placebo group interacted on their primary research outcome. In other words, the two groups paced each other up the mountain, and so it's not entirely surprising that on average the two groups completed the task at approximately the same time. So my point here is, if you're going to do a race simulation, make sure you don't inadvertently introduce confounding factors that can result in you missing the key performance effects. When they looked at incremental exercise in the laboratory to determine VO2 max, they found that the EPO group outperformed the placebo group, unsurprisingly. So, where does this leave us? Which tests should we use and why should we use them? Well, for ramp and incremental exercise tests, for cardiopulmonary exercise testing, and for baseline testing in all sorts of experimental trials, they're absolutely essential so that you can establish the parameters of the aerobic system for subsequent use in other tests. Constant load tests are great to use for understanding mechanistic physiology, but when you set them up, never ever use percent VO2 max, and certainly not percent peak power output to set these intensities, because if you miss where your thresholds are, your physiological responses are going to be all over the place. And peak power output is particularly problematic because that value depends upon the ramp rate of your pretest. If you do a fast ramp, you'll have a higher peak power output than if you do a slow ramp, but all of your physiological parameters will be the same. So please don't use that. If you're doing simulated time trials, you can obviously do performance comparisons, and that performance is more like the real world, but you need to make sure that you familiarize your participants. It is best to use experienced participants in the first place. If you're going to do cycling time trials, use cyclists, because although they might never have done that time trial before, they'll at least know what it feels like, and therefore familiarizing them will be that much more straightforward. You have to appreciate that if you're doing time trials only, the physiological measures you make can't easily be compared between conditions. And so, for my money, what you need to do is, if you're looking at this from both a physiological and a performance perspective, you need to establish the physiology using constant load tests and or time to exhaustion trials, and then you study the performance using simulated time trials thereafter. So if you're setting up a series of experiments, that's the way you do it. An alternative to that is to use a hybrid test, where you have a constant load phase and then you perform a time trial. And in familiarized participants, that can also be useful. And you can make these as long and as short as you want them. So we've done hybrid tests where you do 2 minutes of constant load exercise to get the VO2 kinetics, and then a 5-minute performance trial to understand the performance effects. I've seen others in the literature where they've done 1 to 2 hours of constant load exercise and then tacked a time trial on the end to look at the effect of an intervention on prolonged endurance performance, and that's fine too. And finally, field tests of performance. All I would say here is they're useful and they can be useful, but you need to take great care that you don't introduce inadvertent errors or confounding factors when you do that. So they're much more difficult to control, but they obviously have that level of ecological validity. And with that, I hope you've enjoyed what I've had to say, and if you liked my content, please do like and subscribe to the channel, and I'll see you next time. Thank you very, very much for listening.